Okay, we're back for number 6 on the 2025 released AP Statistics FRQs. We've done the other 5. You can find them on the playlist. I'll link it in the description of this video. And remember, I'm doing this so that kids can see that we're not all perfect and that I'll probably make mistakes on here when it comes time for the scoring scoring roots to come out. And so I doubt seriously I'll make 4s on everything, but I'm gonna do my best. And I'm working with these cold. I've not looked at question 6 before now. So you're gonna see me on here. You can look in the description and click the link for to access the released FRQs from College Board and follow along as we solve this. So here we go with question number 6. Stefan, a psychologist, conducted a study to investigate the effect of time of day on reading comprehension in children. 100 children volunteered. Their parents' consent to participate in the study. 50 of the children were randomly assigned to read a story at 9 a.m. and then answer 25 questions about it. The remaining 50 children were assigned to read the same story at 3 p.m. and answer the same 25 questions. The reading comprehension for each child was measured by a reading score, which is determined by the number of questions that were answered correctly about the story. Stefan is interested in comparing the mean reading scores for the 2 times a day. Table 1 shows the results of Stefan's study. We see a table here with the mean and standard deviation of each group, the 9 a.m. group and the 3 p.m. group, 50 in each group. Okay. Stefan found the conditions for inference were met, so we don't have to check conditions. Conducted a 2-sample t-test. We don't have to name a test for the difference in 2 population means. We're going to let mu m represent the mean reading score for all children similar to those in the study who would read the story at 9 a.m. and let mu pm represent the mean reading score for all children similar to those in the study who would read the story at 3 p.m. Stefan's hypotheses are shown as shown. So he did. This was the 2-sample t-test for a difference in 2 population means. He said H0 was that the mean of the AM kids is equal to the mean of the PM kids. And his alternate hypothesis was the mean of the AM and the mean of the PM kids are different. The p-value for Stefan's hypothesis test was 0.002. State an appropriate conclusion at the 5% significance level for Stefan's test in the context of the investigation. Justify your answer. Okay. We don't have to do all the calculations. They've done all that stuff for us. All they're asking for is a conclusion and context. So part A, this is why I always tell kids to go get the easy points off of question 6 first. So the p-value is 0.02. So we're going to say since the p-value .002 is less than alpha 0.05, we reject the null hypothesis, and the evidence suggests there is a difference in mean reading score for children like those in the study read the story at 9 a.m. and who read the story at 3 p.m. Let me check to make sure y'all can read that. You can. All right. Justify your answer. Okay, that's the conclusion and context tied to the p-value. So that's as much justification as we can do, really. All right, explain why it's appropriate for Stefan to conduct a 2-sample t-test for the difference in population means instead of a paired t-test for the population mean difference. B. Okay. Because each child is assigned to one or the other treatment groups. And children were not paired into any variable could affect the response This was not a matched pairs design. Therefore, a two-sample t-test is appropriate or a completely randomized design. You never know on question 6 if that's sufficient or not, but that's what we're going to go with right now. I like the question now. Let's continue. Part C. Researchers are usually interested in the practical importance of their results as well as statistical significance of the hypothesis test. The practical importance of the results indicates whether the observed results are meaningful in real life. For example, in an investigation of the heights of two groups of students, a difference in the two group means of 3.8 inches is much more meaningful or has more practical importance than a difference in the two groups of only 0.2 inches. One indicator of practical importance is effect size. A common method for measuring effect size for the difference in two groups is Cohen's d coefficient. Cohen's d coefficient compares the absolute value of the difference in the means of the two groups to be pooled variability to the pooled variability of the observed data values from the two groups. Cohen's d coefficient can be calculated using d equals the sample mean from sample 1 minus the sample mean of sample 2, all in absolute value, divided by S sub p, where S sub p represents the pooled standard deviation. X bar 1 represents the sample mean of the first group, and X bar 2 represents the sample mean of the second group. When the sizes of the groups are equal, so standard deviations, S sub p is calculated as S sub p equals S1 squared plus S2 squared all divided by 2 under the square root, where S1 represents sample standard deviation for the first group and S2 represents sample standard deviation for the second group. Consider the summary statistics from Stefan's table in Table 1, studying Table 1. All right, so this is part C1. Ooh, a lot of reading for that one. Calculate Cohen's D coefficient for Stefan's study. Show your work. So the D coefficient is absolute value of x bar 1 minus x bar 2 all over standard deviation of the pool. So we're going to go back up here. And we're going to look at standard deviation. All right, so S sub P, let's look at that again. Okay. S sub P equals the square root S sub 1 squared plus S sub 2 squared over 2. And so we go back to the table and we get D equals absolute value. So 15.2 minus 17.9 all over S sub P, where S sub P is equal to the square root of S1 squared, that's 4.12 squared plus 4.43 squared over, and this was it 2? We'll double check that, make sure. It was. And so let's go ahead and type that in, write that in here. 4.12 squared plus 4.43 squared all over 2. And I would bet they would want us to calculate that. Type it in the calculator. So this is going to equal 2.7 on the numerator. And let's calculate all that in the calculator. So let's do the square root. And I'm going to set parentheses, 4.12 squared. Plus 4.43 squared. Those parentheses divided by 2. All right, so I get 4.2778. I'm going to talk about 2.7 divided by that. I get 0.631. That is D. Let's go back here. All right, we showed the work. Higher values of Cohen's, this is part 2. Make sure you can see still. Yeah. Okay. And so higher values of Cohen's D indicate greater practical importance, and lower values of Cohen's D indicate less practical importance. Typically, we use the intervals listed in Table 2 to help interpret practical importance. There's a Table 2 here in the problem. You can see it if you're accessing it. So based on your answer to part C and the information in tables 1 and 2, table 1, yes, okay, was the statistics. Describe the practical importance of Stefan's results in context. So in the table, it says that a D coefficient of 0.2 to 0.8 is somewhat meaningful in real life. So that in context, we would say the difference in reading scores for children read. Oops, go ahead and put this up again. Let's see that again. At 9 a.m. versus 3 p.m. is somewhat meaningful in real life, according to Cohen's D coefficient. Make sure y'all can read that still. Yeah. Okay. All right, that looks like what we can do there. Part D. Suppose the results of Stefan's study summarized in table 1 instead has standard deviation for the 9 a.m. reading scores S1 and standard deviation for the 3 p.m. reading scores S2 that were both greater than 4.43. Assume the group sample size and the means are not changed. Would the Cohen's D coefficient in this new situation be smaller than, larger than, or the same as Cohen's D coefficient calculated in part C1? Explain your answer. So the only thing changing is that both standard deviations, S1 and S2, are larger. And we want to compare the effect, how that would affect Cohen's D coefficient. So if both of these were larger than 4.43, S sub P would be larger. The means didn't change, so the denominator of the D coefficient would be larger, which would make the D coefficient smaller. So C part 2, let me make sure you can read this, or C, D part 1. Go ahead and do this. If S1 and S2 were both larger than 4.43, then SP would be larger. Explain the math behind that because the numerator is larger. If everything else remained the same, denominator of D would be larger, causing D to be smaller. Okay. We're going to leave it at that because I think we could get really wordy on that if we try to get too detailed. Does the Cohen's D coefficient described in part D1 indicate that Stefan's observed difference in the means in a new situation would have more practical importance than, less practical importance than, or the same practical importance than as what was originally determined in part C2? So about that up again. This was 0.631. It would make the D coefficient smaller. So 0.631 is toward the upper end of the range for the somewhat meaningful in real life. So depending on how large, how much larger than 4.43, it could be, well, it'd still be less meaningful because it's getting smaller. It is getting smaller. Okay. So let's go back to that. As D gets larger, table 2 indicates practical importance increases. Sure you can see this. Yes. And D1 D1 D got smaller, which indicates practical importance decreases. Therefore, in the situation described, in D1, the observed difference would have less practical importance. Than was originally determined. All right. That's the end of question 6. Stop. End of exam. We'll see how I did after the scoring rubrics come out this fall.